Right here. This session is going to focus on aircraft turns, which obviously can take two distinct categories. We've got vertical turns and the standard horizontal turns to have a quick look at. Right, there's a series of sessions on aircraft maneuvers. This is one of the key aircraft maneuvers, obviously. An aircraft obviously needs to change its heading if it wants to go to a different airport. Otherwise, it would just end up climbing and going in a straight line. So the aircraft turn is a key fundamental aspect of control. The pilot will input some rudder and aileron input in order to turn the aircraft or change its heading. And then, as I say later on, there's a special case for vertical turns to look at. Right, so first part, we'll look at balanced horizontal turns. Balanced horizontal turns refers to the aircraft being in a constant altitude. So although we're changing the forces for the heading to produce a new direction for the aircraft, what we're not doing is climbing or descending in this session. Obviously, this will make our calculations a little bit more difficult to consider. Right. Aircrafts or pilots need to know some set criteria in order to help them fly the aircraft. Obviously, I've got two stated two here. There is actually three worth pointing out. First one speaks for itself. It's the rate of turn. Obviously, if the aircraft's going to start turning, it's the change in its heading. It's going to have a rate at which it does it. So how many radians or how many degrees is it doing per second? And we've got the turn radius. The third one, which is sometimes considered, is also something called the G loading. If you're familiar with roller coasters, this is probably where I might have heard of G loading before. Basically, times the mass by gravity would give you the weight, but if you're pulling 2G, you feel that twice as heavy than you actually are. Right, couple of diagrams to look at. We've got two diagrams. Left one showing the aircraft's in a head-on process as it starts to turn through a horizontal bank. This right-hand diagram is the same aircraft, but it's a top-down view. So obviously you can see the different forces involved and the concept it's going in some form of rotation. Right. What I'm going to do is very quickly jump out of this and we'll discuss the diagrams in a little bit of detail and talk about the key points that we can get from these. Right. First thing I'm going to do is consider the forces acting vertically and horizontally. So this is going to start looking at this diagram on the left initially. So the head-on view of the aircraft itself. If we have a look at the vertical forces involved, something about its center of gravity. So this is the point of origin, if you like. We examine the forces. We're going to add them all together in a perpendicular direction to this dashed line, or if you want, you can get rid of that and call it a vertical. Right, what we've got going up is half of the lift component. So this aircraft is now got in a bank. The lift vector is actually acting at the set angle. Part of this lift is going to start pushing the aircraft in that direction, and part of this lift vector will push it in that direction. So upwards, we've got a component lifts because of the bank angle. So this Greek letter phi here is the angle of bank. And the cosine comes from just using basic trigonometry. Right angle there, lift being the hypotenuse. This is the adjacent, so the cosine. This one being the opposite gives us the sine of the angle. Right. Equally, this lift vector or lift component, because of the bank, needs to balance out the weight of the aircraft. In a horizontal turn and in a balanced horizontal turn where the altitude doesn't change, these two vectors will cancel each other out and sum to zero. Right, first up, I'm going to rearrange the equation for the weight. So it says weight equals lift times the cosine of our bank angle. And the first concept I'm going to introduce here is something called the load factor or the G loading. G loads or the load factor. This is given the letter N for November. And its statement says it's the lift divided by the weight. So in horizontal flights, straight and level, N would equal 1 because the lift would balance the weight. So you're dividing the same two numbers together. Right. If we use this principle, what I'm going to do is with this equation, divide both of them by the weight. The weight divided by the weight equaling the lift, the cosine and the bank angle divided by the weight. We should be able to see here that on the left hand side, whatever the weight is, dividing by the same number, that will give you 1. On the right hand side, we have this magic ratio of the lift divided by the weight, which gives you N. And of course, the bank angle hasn't changed. Right. First, remember the three things we need. We are looking for the load factor, the rate of turn, and the turn radius. The best equation you can come out with is for the load factor for a horizontal balanced turn, which says load factor 1 over the cosine of our bank angle. Right, this is quite an important feature. If I jump back into our PowerPoint here, and our formula. Right, this statement at the bottom. The relationship of the load factor is independent of the aircraft. It doesn't matter what you're doing. It doesn't matter where you're pulling it. But basically, if you're at a bank angle of 60 degrees, you will be at 2G. That doesn't matter whether you're in a 737. It doesn't matter whether you're in an F-15. Both aircrafts at 60 degrees will give you 2G or 2 times our weight. Right, if you're not happy with that, 60 degrees, cosine of 60 degrees in the calculator should give you a half. 1 over a half is actually 2. So N would equal 2 in that case. Right, there's the first of the key equations. Right, so get rid of all of that. and start to analyze the other bit. In the second diagram, there's a couple of things to point out. This lifts component pointing towards the center of our circle, our rotation, is this vector here. Right, and obviously because this aircraft has both a linear velocity and a rotational velocity, Greek Latin omega, it starts to produce a centripetal force. This equation here, mv squared over r, is the fundamental equation for centripetal force. It is going to come back into this very shortly. Right, get rid of all our scribbles off here into the next bit. Right, in the previous section there, we summed the forces vertically, so that was the lift of the cosine with the weight. This time, I'm going to do the same thing, and I'm going to do this in the horizontal direction. Right, looking at things going horizontally, or in that way, on the first diagram, we will have this vector here from the lift times the sine of the bank angle. You can see here that was equal to our centripetal force. Right, and the third one, very quickly introduce, is the same equation, same centripetal force, but in terms of weight. Remember, mass times gravity equals the weight. So that equation can be written as the weight times the velocity squared over gr. Right, these equations here are what we're going to run with as we start to go through this. So if we look back into the left-hand diagram, take this triangle here, have a closer look at it. We've got it looks a little bit like that initially. Right, first up, we've got the lifts vertically. Its component was clearly stated as that. Remember, this is the weight as well. It needs to balance out this vector here. This sine over here can be written in terms of the weight. Not drastically important, but it does come back in a little bit later on here. This weight here, if you take this in terms of trigonometry again, but this is your reference side rather than the lift this time, this weight, based on the angle of bank, is now opposite, adjacent. There's our angle. So that can also be written in terms of the weight, which is the weight tan the angle. Right. I've deliberately done this because when we start to, this is going to be the fundamental equation here in green. When it adds a third section to this, there'll be another equation coming in here that we're going to use to go later on. Right. So based on this right angle, this red triangle here, from Pythagoras, a squared, b squares equals c squared. So in terms of our terms, we've got a squared being the weight, weight of the tan squared will equal the lift all squared. Right. Deliberately written like this because what's going to happen is if we divide through by the weight, but though it's going to be the weight squared here because it's all squared terms. It's a little bit weird to process this. So dividing all of that by the weight squared, we get weight squared over weight squared. W tan all squared over weight squared, and the lift squared over the weight squared. Right. Two of these are fairly straightforward to look at. Weight squared divided by weight squared, it's the same number on top as it is on the bottom, so that's going to give you 1. This one over here, it's lift divided by weight. Even though they're both squared, the square term will cancel each other out here. That will give you n. All right, in this one, the weight squared will cancel this weight squared out, leaving us with tan square theta. All right, tan squared theta with a bit of rearranging is equal to n squared minus 1. You take the square roots of both sides like that. Right, lastly, square root of tan squared is just tan of the bank angle. N squared, I'm going to be leaving that in the square root, although it can be separated out. Right, this doesn't account for the weight yet, so this is where it gets a little bit weird, although we've cancelled all the weight back out. What I'm going to do is multiply both sides by the weight, which gives us W tan phi, or W times the bank angle, the weight times n squared minus 1, all square rooted. Right, because this is now in terms of the weight, what that actually gives us there in terms of the weight is this bit here. W tan phi is the same as L sine of the bank angle. It's the whole point of doing that. This makes this bit here, zoom out and see it, makes this bit equivalent to this bit here, which as you can see here is also the same as the lift times the sine of the bank angle. We're just starting our equation off. Right. So the final part of our equation here, lift times the sine of the bank angle, the centripetal force, mass, and weight versions is also weight in squared minus 1. Right. A little bit more on the proof. We're nearly done. I'm going to take this bit to run with. Right. As I say, this is all very weird because even though you just multiply it by the weight to get it back into that form, first thing I'm going to do is divide by the weight. Both sides here. So dividing through by the weight leaves you with the velocity squared over gr equaling the n squared minus 1, load factor minus 1. Right, first off, rearrange this for the radius. This is the second of the three things we want. Fairly straightforward. The radius goes up, leaving you with that on the left hand side. This big square root comes down. This is equation number 2, if you like, because it's the second of the three things we want. Right, and lastly, I did hint at this further up. When we go around the circle, we have both linear and angular velocity. So here is a relationship that says radius radius is linear velocity over angular velocity. Substituting this into here, the then radius, we get the relationship. We rearrange this for the angular velocity. So the first thing to do is flip the equation over. When we do to the left, we have to do to the right. And multiply up by the linear velocity. You see the angular velocity, and hopefully you can see there's a velocity on top, velocity on the bottom. That will cancel its power out. So our end equation here, let's say gravitational or acceleration due to gravity multiplying the square root of the load factor squared minus 1 over the speed of the aircraft will give you your rate of 10. Right, remember, rate of 10 is in radians per second. All right. There is some examples in this session, but very quickly go through them. This first one's a little bit tricky because you don't really get given much. I'll show you how to start and I'll stick the solution on. You're asked to find the load factor, right angle, turn radius. If you are at a speed of linear speed of 203 feet per second, a rate of turn of 15 degrees per second. Right. First off is remember the rate of turn has to be in radians per second. So the rule says every circle has 2 pi radians, but it also has 360 degrees. That is your starting point. Right, I want to know what 15 degrees is in radians, so what I'm going to do is find out what 1 degree is. I'm going to go 2 pi, divide that by 360. I now know what 1 degree is. And I'm going to multiply this by the angle we want. So 15 times 2 pi 360 is the equivalent of 15 degrees, which is about 0.262. Or if I believe correctly, that's about 1/12 of pi. All right, the rest of it is basically identify the 3 equations and tick off what you know, what you don't know, and then you'll probably find out there is one formula that you can use. Right, so easy solution very quickly. Rate of 10. You can rearrange this formula. So this is the tricky bit. You know the rate of 10. We know G. We need N, but we've got the speed. So it's rearranging this for the load factor. So your formula said rate of 10, gravity, n squared minus 1 over V. Right, rearranging this, the first thing we want, because we want N, is on top of the fraction. Yes, it is in this case. It's on the numerator. The next step is to isolate everything around it. So the first step needs to be to get rid of this velocity. It's currently dividing our values. We're going to multiply it. So we're getting the rate of 10 times the linear velocity, gives us G n squared minus 1. Next up, before we can get rid of the square roots, we need to get anything attached to it. This G value is currently attached, so this needs to go. It's currently multiplying, so we need to do the opposite, which is to divide through by G. Right. Only once we've got the square root or the function on its own can we do the inverse of it. So the inverse of a square root is to square both sides. Right. We will after n on the load factor. So this needs to stay on its own. It's positive, so we need to get rid of anything else on that side, which is the minus 1. The opposite of subtracting 1 is to add it. So Angular velocity, linear velocity over g all squared. We're going to add 1 to that value will give us the load factor all squared. So your final step is to square root both sides, get rid of the square of that one, we'll square root that side. Right, I've shown you that because there's nothing working here. So there's the rearrangements. There's the answer. Just plugging the numbers in. Remember, it's feet per second, so G is not 9.81, it's 32.2 feet per second squared, the imperial version. The rest of them just fall into place here. Right. Turn radius, you can either use the formula or you can use the relationship set that said rather. The turn radius was from earlier on. The linear velocity over the angular velocity, of which you've got both. So you can prove that. 203 divided by, this was 0.262. You stick that in the calculator, you should get roughly the same answer. It's all about rounding, obviously. And the slight inaccuracy of 32.2. If you go 203 divided by 0.262, 774.8. Right, as I say, that slight difference, very close, but slight difference. There's a few more decimal points on that. And it's all about what accuracy you put N in as well. Right, finishing them off. Bank angle, we know the load factor. You can very quickly get the bank angle by rearranging it. So 58.8 degrees. And that should answer our question. Right, moving on to the vertical turns. So this time, horizontal turns, remember, we're rotating about the vertical axis in which we can change the heading. Vertical turns involve pitching the aircraft up. It will change its altitude, and if it's going fast enough and it's able to do so without stressing the aircraft, we will complete a vertical loop. Right, so there's 3 steps, but 2 classifications. You can be in the pull-up phase or the pull-down phase. Right, so vertical turn. This is where the analysis is going to come from. Vertical turn initiated by the pilot pulling back on the stick. So the pilot pulls back on the stick. We change the position of the nose. Its aircraft will start to climb. Right, phase number 1. This is the aircraft at the bottom. The pilot, like I just said there, has pulled back on the stick. And when we analyze this, we only consider those perpendicular to the velocity. Linear velocity this is. So if the heading is there, the linear velocity is going in that direction. We're only interested in forces going that way and that way. Right, so summing our forces, we've got a lift force going up, a weight force going down. And remember, it is in a loop or a circle, so it will have a centripetal force involved as well. Right. The same process is going to apply all the way through here. You're going to take your sum with the centripetal force. We're going to divide through by the weight. This will be the same steps in all three stages here. Divide through by the weight. Lift over the weight, weight over the weight. Our centripetal equation over the weight. Right, look carefully. Lift divided by weight is our definition of the load factor. We subtract 1 because weight divided by the weight is 1. This is equal to the velocity squared over gr because the weight will cancel out there as well. Right, so same three equations. N, v squared, gr plus 1. They're easy to identify some of these. So the horizontal equations all had square roots involved. The vertical ones have none. Pull up has the load factor contributing to the load factor, hence the plus 1. We use the same relationship that said the radius was linear velocity over angular velocity. Make that substitution with a bit of rearrangement. And we come out with those two equations. Right, so n was v squared over gr plus 1. Right. If you read the top bit, it then says summation of the forces performed at 3 distinct 90-degree intervals. So this aircraft goes 90 degrees through the loop to vertically up. Remember, it then says we're only interested in things acting 90 degrees to velocity. So there's v. We are interested in that direction, of which you've only got the lift in this case. When you sum the forces this time, you get the lifts and the centripetal equation in terms of the weight. Divide through by the weight as we did in the last step. So lift divided by weight is the centripetal equation divided by the weight. Lift divided by weight was the definition of the load factor. Weights cancel out. There's equation number 1. Right, you can rearrange that for the radius. Which is b squared gn. And if we use that relationship, the rate of turn in this case is g over n, flips it over v, cancelling out that. Right. Lastly, there's only 3 stages to this because once we've gone another 90 degrees, the stage after that is exactly the same because the lift is the only horizontal force. So this particular diagram refers to whether the aircraft's going vertically up or vertically down. The final stage is 180 degrees after the pull up, which is the pull down. This is the strange notation that lift isn't always a useful force because when we sum this, there's the aircraft velocity again. We want anything going in that direction. So we've got centripetal force. This time, You've got the lift and the weight acting in the same direction. Right, divide through by the weight on that side, divide through by the weight there. You'll find out that those two cancel out. So you've got the velocity squared over GR equivalent lift divided by the weight being load factor, weight divided by weight being 1. So this time, you get the negative G loading because we're subtracting. All right, with the same relationship, you can get radius with a bit of rearranging of this equation here. Says the radius is velocity squared. We'll divide through by n. All right, and applying the top equation, we flip everything over, so we get g n plus 1 over the velocity, because we'll cancel out this term. We'll give you the rate of turn in this instance. Right. The solution, there's another question here that deals with vertical turns. Solution refers to the fact the aircraft's pulling up in this stage. There's a little trick involved, just to point this out. There's the working. So it asks you to calculate the height at which you need to pull out. So the aircraft will be coming down in a gentle descent. What point do you start to pull out, pull up? So in this instance here, we've got this rate of turn. Right. The concept here, or the trick, is because it's a circle, or part of a circle, the arc length here, all of that length there is the radius, and all of that length there is also the radius. This bit here, extend this line now, this bit is a right angle triangle, which, you know, one of the angles is 45 degrees. So we can actually physically work out that length. So if you can work out the radius, we know that length is going to be exactly the same. Using this right angle triangle, we can then work out what this portion is, which is that calculation there. And then you can subtract the difference between the two. So we've got 700s minus this length here, leaving the 227 meters, that length there. Right, there is one last thing to quickly look at, which is the Venn diagram. It applies to both vertical turns and horizontal turns. So it's everything we've done merges into one here effectively. First part of the diagram, the aircraft will take off, it will climb. The limiting factor is the stalling point. So this is basically the lift equation here. Right, obviously, we assume the aircraft's in the air. It can go, in this particular example, it cannot reduce or go below point A. This is the stalling speed for any maneuver in the air. Whether you're doing a positive load or a negative G load, so an upside down scenario. Obviously, the faster you go, the lift curve continues and continues and continues and continues. It's parabolic because of the square term. It'll just continue like that. Right. Once you get to a particular point, you notice as you start to bank the aircraft, for example, it will start to produce more and more and more G loading. There is a finite point in which we can operate. We'll do positive G loading or negative G loading. If you go above that, we will damage the structure. It's not fatal, but it might cause some serious damage which needs to be repaired. If we keep on going, it will enter this red region. As you can see, is the structural failure. It will cause something to break off the airframe, no doubt, and you'll plummet to the ground. Same with the negative G loading. Right, the other thing you might not even have to pull a maneuver for, but if you continue your speed, happy days. Notice it's load factor's 1 for steady level flight. You can keep going and keep going and keep going. There will then be a point where we have some problems. Right, it says maximum structural cruise speed. This particular point, there's several things that can occur. One, assuming your engines can produce enough thrust, you may start to induce a shockwave. Obviously, the introduction of a shockwave at any point in the aircraft will produce a huge amount of drag. It will spoil the lift and obviously start to stall the aircraft. In addition to that, shockwaves actually cause damage because the insane amount of pressure changes. Number 2, going into the dynamic analysis module, you hit a particular speed, you will get aerodynamic flutter. Remember, if you keep going faster and faster, that will lead to aileron reversal, a very unfavorable condition. And then obviously keep going, keep going. The flutter introduces more and more energy. It will start to break things off the aircraft again. Right. The final point where to point out on this is point B here. It's the corner speed. This is often referred to as the maneuver speed. It is the slowest possible speed. So remember, this line here is the stalling point. But it's also pulling the maximum G loading, because if you go any higher than that for the G loading, we cause structural damage where we don't want to go. So point B is the slowest speed at the maximum value of N. And we've got a little equation here. It's basically the lift equation rearranged to determine how to calculate that. Right. You may be asked to sketch this very quickly in an exam. It doesn't need to be a work of art, but it's basically ensure you've got a safe operating region, caution range, structural failure range rather, stalling points, and being able to identify the maneuvering / corner speeds. Right, that is the end of horizontal and vertical turns.